Dobry wieczór Państwu. Trzeci dzień Copernicus Festival, tajemnica dobiega końca, ale zanim nastąpi koniec, to mamy jeszcze ostatnie wydarzenie. Zanim jednak przedstawię ponownie naszych gości, przypomnę, że partnerem Copernicus Festival jest Małopolska Organizacja Turystyczna, która objęła patronatem dzisiejszy dzień festiwalu poświęcony tajemnicom kosmosu. Projekt jest dofinansowany ze środków budżetu państwa przyznanych przez ministra nauki i szkolnictwa wyższego. Dofinansowano go ze środków ministra kultury i dziedzictwa narodowego pochodzących z Funduszu Promocji Kultury Państwowego Funduszu Celowego. Partnerem wydarzenia jest miasto Kraków, a Copernicus Festival został objęty honorowym patronatem ministra nauki i szkolnictwa wyższego oraz prezydenta miasta Krakowa Aleksandra Miszalskiego. Przed chwilą wysłuchaliśmy wykładu profesor Ruth Durer, która jest naszą główną gościnią dzisiejszego wieczoru. Przypomnę, że profesor Durer jest szwajcarską kosmolożką pracującą na Uniwersytecie w Genewie. I będę również dzisiaj rozmawiał z profesorem Uniwersytetu Jagiellońskiego Sebastianem Szybką, pracującym w Obserwatorium Astronomicznym UJ. Let me now switch to English. Before I switch to English, przypominam, że że nasza rozmowa jest symultanicznie tłumaczona. Jeśli ktoś z Państwa nie ma zestawu słuchawkowego, może go pobrać tam z tyłu sali przy wejściu. Okay, back to English. I promised that the audience will have the opportunity to ask you some questions, but first let me ask just a few questions and then we'll move to audience, I promise. At the end of your lecture, you've mentioned those new preliminary results of DESI, which suggest that cosmological constant is not really constant after all, but it decreases over time. Let's assume that this result holds. What would it mean for our understanding of dark energy? I mean, would it mean, for example, that the interpretation that this is vacuum energy is no longer tenable?
Yes, it would mean that the dark energy is not vacuum energy, because if it is vacuum energy, then it's, let me be just for a brief moment a bit technical, its energy momentum tensor must be proportional to the metric, which would mean that the energy density must be the pressure must be minus the energy density exactly. Otherwise, it's not vacuum energy. Otherwise, it breaks the symmetries of the vacuum. Otherwise, it defines a time evolution. And then what it could be a scalar field. What is a scalar field? You probably all have heard about the Higgs particle. All particles in physics are described as fields, and a particle with no internal angular momentum, no spin, is a scalar field. It could be such a scalar field. However, if we take not only the fact that it is evolving seriously, but also that the parametrization which DESI has investigated is the correct one, then it cannot even be a scalar field. Because such a scalar field has that the sum of energy density plus pressure must always be positive. And if you look at this parametrization which they gave us for their best fit values, this actually becomes negative. And therefore it cannot even be an ordinary scalar field. And for me, I'm not taking this parametrization at all serious, because there were people who fitted the data with the scalar field and they got a fit which was not much worse than this WOWA fit from the DESI people. But then the most natural way how to get some seeming negative pressure which is more negative than the energy density, this can be obtained easily in theories where you modify gravity, where you modify general relativity.
Sebastian, do you want to add something?
So I have a question related to what you have said, because it's often, I think, that it happens in science that if we don't know things well, we think it's like one simple thing. And then there's another option that maybe this dark energy is like a cosmological constant plus some kind of other effects or something other. So what do you think about such possibility?
That, of course, is also a possibility that it would be a part of it would be a cosmological constant, and there would be another part which would be dynamical and evolving. But again, also in this case, this other part could not be simply an ordinary scalar field. There are scalar fields from scalar tensor gravity theories which could do the job, but not a normal scalar field like the Higgs field or so.
So in other words, what you say implies that maybe Einstein theory meets its limits in cosmology, yes, if this kind of effect will hold.
Before I would bet on that possibility, I bet on the possibility that the data has some dynamical problems in it, which we have to come to grips with. And this data analysis is quite challenging. And it's the first time that we have so precise data. You know, if you have data with large error bars, then it doesn't matter if your analysis is not so perfect, because the statistical error is still large and you don't see the error in the analysis. But if the statistical error becomes small, your data is very precise, then you must make a very precise analysis not to draw wrong conclusions. And I think this we still have to learn.
And do we think that in 1 year from now, with the new Euclid data, so will it solve the problem or just give more hints or more secrets? What's
That's a good question. If I only knew the answer.
Okay.
I hope,
We will know in 1 year. Or how long does the Euclid mission is designed to last?
It's designed for sure 3 years. It could go 5 years. It has enough. It needs very, very little fuel because it's designed to need very, very, very little. So I think it could still work passively for 6-7 years.
Okay, that's
but
not
there
too
is
long.
a hope that it will release data, not after the end of the mission, but during the mission. This is what such missions do.
Okay, so maybe before we delve into possible alternatives to Einstein's theory of gravity, let me ask you one more question about what if. What if this preliminary result of DESI holds? Because you've mentioned in your talk that now we have this standard cosmological model, this lambda CDM model, which assumes that dark energy is constant, that dark energy is described by cosmological constant. If dark energy turned out to be dynamical, how would it change, for example, the age of the universe, right? Because when we say that the universe has 13.8 billion years, of course, this is what this standard cosmological model tells us. So if this dark energy decays over time, would it change this estimate of the age of the universe or not really much?
It would change it, but not more than 3-4% or so. So I don't think that everybody would care too much about that. It wouldn't change very much. It would change probably the future, because if dark energy really evolves the way the DESI data has parameterized it, let us take this once for granted and say, okay, that's the correct. Somehow there is a theory which gives exactly this kind of parameterization also into the future. Then dark energy will disappear in the future.
But would it mean that the universe would stop accelerating and then start contracting in this scenario?
That depends. It would stop accelerating, yes, but it might not be contracting. It might expand forever, nevertheless.
Okay, so the universe would still be rather old, over 10 billion years, and also the details of this thermal history of the universe you've presented during your talk. This would more or less still be everything would be valid. It would not be like a complete revolution in cosmology.
No, all of this would still hold, because the thing with dark energy, since even if it is evolving, it is so slowly evolving, and it's not getting much denser as we go into the past. So as soon as we go into the past, redshift 2, 3 or more, we can forget about it. It's just a small correction to everything else, and it gets less and less important the more we go into the past. It gets more and more subdominant, so it doesn't change very much the past. A little bit, but very, very little.
Okay, so it would be a revolution, but not a total revolution. Okay, so maybe let's get back to those alternate theories of gravitation. I've read on Wikipedia article on you that one of the things you're doing is massive gravity. Can you say something more about this? Because from what I understand, this is an alternative to Einstein's theory, right? In Einstein's theory, gravity is massless, whatever it means. Can you say something about what massive gravity means?
Yeah. In Einstein's theory, the graviton is a massless particle, like the photon. It's a particle which transmits gravity, but which has itself no mass. Now, it's not so easy to give the graviton a mass. To give it a mass, one has to introduce a second metric. And so the difference between these two metrics can behave like a mass term. Now, the most elegant theories of massive gravity, in these, also the second metric is dynamical. And you can have such universes which behave like dark energy, which would fit the present data. But the mass would have to be ridiculously small, would have to be some more than 20 orders of magnitude smaller than all the known masses which we now have for elementary particles. Of course, we would have to fine-tune it to have exactly the right value. So I don't say no to everybody who says these theories are not very natural, and they probably are kind of effective field theories which break down also at relatively low energies, and we don't know how to correct them. So they have all kinds of theoretical problems as well.
Okay, but let's now maybe get back for a moment to cosmological constant, because of course there are also alternative theories to dark energy. Sebastian, I've heard that some time ago at least there were theories that tried to explain dark energy as a sort of illusion caused by inhomogeneities. I mean, usually we assume in the standard cosmological models, we assume that the universe, when we look at it at the largest possible scales, it's more or less uniform, it's homogeneous. But it turns out that if we do not assume that, we can get an effect which works kind of like dark energy. Is it still a thing? I mean, has it been disproven, or is it still probable?
So people were working on that for many years, but Professor Dürer, together with Julian Adamek, I think, they said that they were wrong.
Okay, so it's
They wrote a paper, I think the paper, it was 3 years ago, maybe, yes. So
you killed it. You killed it. You killed this theory.
Using numerical simulations. And of course, nowadays we know that there is effect related to inhomogeneities of the universe, but it shouldn't mimic cosmological constant, and it's rather small. So it's like a correction to the model we have, not the order of magnitude effect that is needed to explain cosmological constant without dark energy without cosmological constant.
No, but wait. A few months ago, I've read some spectacular news. Maybe that's because of the news, not because of the actual science behind them. But there was a kind of a revival in this so-called timescape cosmology. Like that there were news that some relatively new theory, which also assumes that we shouldn't assume the universe to be perfectly homogeneous. They can explain. Well, the observations, the cosmological observations, slightly better than the standard cosmological model can. Has this timescape cosmology has also been disproven by the paper you've mentioning, or it's something different?
So this timescape cosmology, I think, is David Wiltshire
Yeah.
from New Zealand. And I'm not expert on this model. Maybe Professor Durer want to comment on that?
I'm also not an expert on this timescape. It's rather complicated, but I can't. I must admit, I can't truly understand it, because if you write down Einstein's equation, of course you could have completely inhomogeneous universe, but look at the microwave background. It's so homogeneous, so isotropic. How can it be so isotropic if this timescape idea is correct? And even, if you say, okay, fluctuations have evolved later, at least at the time of recombination, fluctuations were very, very small. So perturbation theory cannot be completely wrong. And it tells you how these fluctuations evolve until they become of order, let's say, 0.1. That would have been very late in the universe. Of course, you could say also dark energy is very late in the universe. But still, if we do our numerical simulations and try to simulate GR on large scales, we do find, as Sebastian said, deviations from the perfect redshift distance relations, but these deviations are of the order of percent and not as big as we need to explain dark energy.
So I would like, if you don't mind, to come back to general relativity, just plain general relativity, and to another tension in the standard cosmological model. There was no time during your lecture to mention that, but the Hubble tension. And this tension seems, because the problem with cosmological constant or dynamical dark energy is like a new thing. It's from April. And the Hubble tension is much older. It's already like 15 years old, and it's much better established tension.
Yeah, but can you remind what Hubble tension is?
Okay, so I will briefly remind. So there is this speed of expansion of the universe given by the Hubble constant. And this Hubble constant can be measured directly almost now, I would say, with supernova, like local observations. But in the cosmological model, when you analyze the CMB background, so this initial radiation, we have map of it from Planck, then you can predict from that what kind of expansion speed we should see now. And for many years, when the observations were not precise enough, there was agreement. But then, like 15 years ago, the error bars become smaller, and they stopped to agree. So that's why we have tension. So one number is like 68 from the CM, or 67 kilometers per second per megaparsec. This is how we measure the Hubble constant. And the other result is like 74 or 73. So no big difference, but
they're still close,
below.
but okay.
Yes. And it's extremely interesting because this result, it doesn't want to go away. As you said, there were many results in cosmology, many tensions that with time, like this sigma 8 tension, it's weaker now. But this Hubble tension, it is still there. So what's your opinion on that?
Yeah, maybe let me first, before I say what I think about it, say a little bit more. It's true. If you calculate, if you fit the data from the cosmic microwave background, which is kind of the simplest data we have, then you get that the Hubble constant should be of order 67, 68 kilometers per second per megaparsec. So this expansion speed for galaxies which are 1 megaparsec away should be of order 68 kilometers per second. If you measure this distance redshift relation with the supernova along the diagrams which I have shown you, then for the closest supernova, you will also get this constant which relates the velocity to the distance, and you get 73 to 74. The thing is, not only in the CMB, but also if you look at galaxy clustering via these so-called acoustic peaks, you also get 68. And these galaxy clustering measurements, some of them are as close as many of the supernova results are. So it's no longer entirely true to say, okay, it's the CMB far away, which give you another result, and the supernova close by, which give you another result. Also, these baryon acoustic oscillations, which we see on redshifts of 0.2, 0.4 up to 1, give you the same result as the CMB. Now, what is happening here? I was also always very concerned about it because this is a deviation, or this is a disagreement of 5 standard deviations. So the error is very small. The probability to get one to see one if the other one is true is like 10 to the minus 4 or 10 to the minus 5, really very, very small. Now, in this camp who does the supernova measurements, there are now actually 2 big camps of great experts. One is the camp of Adam Rees, who gets always 73, 74. But then there is also Wendy Friedman. She is also somebody who is doing this supernova business since 20, 30 years. And she says that, that there are that the normalization of this supernova is actually not entirely clear, and if she normalizes them with Cepheids or with some kind of tip of the red giant branch stars or with some other type of stars, she gets different results, which actually vary from 69 to 73, and so I would say the problem is already between the experts of the very nearby supernova. They already have this problem among themselves. And therefore, for me, I think the problem there is with the systematics. Of course, it could still be that the measurement of the CMB and of the baryon acoustic oscillations in the galaxy surveys is wrong. But this measurement is so much simpler to interpret than the supernova, which have to be gauged by nearby Cepheids or by some nearby distance ladder. And if that gauge is wrong, then everything is wrong. And since the experts among themselves don't agree, I think, okay, let them make up. This is no longer my business.
So you're saying that those standard candles aren't so standard after all?
Yeah, that's a good way to put it, yes. The supernova might be still really reasonably good, but you have to get the absolute luminosity by looking at galaxies where you see also Cepheids. And then you get a certain absolute luminosities. And then you look in this galaxy, let's say you have also, say, tip of the red giant branch stars, and then you get again another distance. And so these distances seem not to agree very well.
Now I think about a question, maybe it's a silly question, but I'm not a cosmologist, so please correct me if I'm wrong. Could gravitational waves from merging black holes help here? Because I've heard, maybe I'm incorrect here, that also you can use those merging black holes and the gravitational waves as not standard candles, but they say standard sirens.
Yes.
Maybe they can help.
Yes, that's very exciting, and that probably will solve the problem. But that's going to take time. It's going to take another 10 years. We need something like Einstein telescope. But the reason is the following, the simplest objects which we have in the universe, the simplest object is a black hole. And the second simplest object is 2 black holes. So there we can more or less know everything. We can calculate things very well. We know the response functions of our telescopes really well. There we have much less complicated cookbook physics as we have with red giants and Cepheids, which are so complicated objects, or supernovae. The thing is, for the black holes, we can measure very well the distance they have from us, from the luminosity which we receive. We call them sirens because we see them in frequencies of about 100 hertz or so, which are actually audible frequencies. So we can actually translate the gravitational radiation into a sound by just using this frequency. That's why people call them standard sirens. But if we then will correlate them with galaxy surveys, because these black holes are in galaxies, and for the galaxy surveys, we can measure very well the redshift, so we will get an extremely good redshift distance relation. If we have sufficiently many of them. We need a statistical sample for that. Now we have order 100, but we will need order 10,000, and that we will have with Einstein telescope, but not before.
But there could be even easier way with neutron stars, yes? When you have the direct electromagnetic radiation that gives you redshift. But so far we have just one event.
Exactly. There, I agree. That would of course be the best. But there, even with Einstein telescope, we probably will have 30 events. I think the other method, correlating with galaxy surveys, will be more powerful just because of the statistics.
Okay, so what kind of telescope do we need to solve this question? You've mentioned this large-scale survey, that's correct?
Yeah, we will correlate gravitational waves, which we will measure with Einstein telescope, which so far is only on paper, but it's a European project. So the Italians want it in Sicily. The Germans want it somewhere near Grozny, near the Polish border, I think, actually. And Dutch also want it somewhere. And each of the countries says, we only pay if it comes into our countries. That's how Europe goes, you know, with these scientific projects. So let's hope it's going to be built. And if it is, this will be much, much better than LIGO and Virgo together, which we have now, which are also already wonderful. But we need to make one step further in the precision to go deeper into the universe. You know, LIGO and Virgo, they can never see as far as we have to see. We have to see, to measure this distance redshift relation well, we have to see gravitational waves out to redshifts of order unity. Now we see them out to redshifts of order 0.05. That's just not enough.
So maybe let's clarify, because this name telescope, it could be misleading here, because this is the gravitational wave detector, in fact. So it's works in a different way than the standard telescope. So it's not the tube.
It's even an underground facility. So,
yes. So now astronomers work underground. Yes, that's a new thing.
And also, there's still this project about launching a gravitational telescope into space, this LISA project. Is it still, I mean, I think it was cancelled some time ago, but then it was revived. So the idea is to, because gravitational telescopes, if you know, they are interferometers, which means they are very big. They have like arms whose lengths are in kilometers, 4 kilometers, I think, LIGO, right? So it's still too short to make gravitational wave observations. So there is an idea to launch like 3 probes that will form a triangle whose sides will have 2.5 million kilometers long, and this will be like a giant gravitational wave observatory. But I think it's still far away in the future.
Not so far away. It should fly in the beginning of the 30s. It's in very good shape. The pathfinder for this experiment for this satellite, LISA Pathfinder, has been extremely successful. But this will measure gravitational waves with much lower frequencies. It will be very interesting for example, gravitational wave background from the early universe, which has stretched to very large wavelengths and low frequencies. And it will certainly measure gravitational waves from the big black holes, which are in each galaxy, there is a big black hole. Also in our galaxies, there's a black hole of about 1 million solar masses. And when galaxies merge, these black holes probably also merge, and they emit gravitational waves in the right frequency band for LISA to see. But of course not these binary black holes which LIGO sees. So this will be millihertz, while LIGO works in 100 hertz frequency band. It's a completely different frequency band and correspondingly different physical processes which will be seen.
And maybe we should clarify for audience that the Pathfinder mission is just a smaller version of the instrument. So it was already in space, and they showed that it can work. So in fact, the idea is good. Now it should be.
Yeah, one of the very technical difficulties of this is having these gyroscopes to orient this very, very precisely. And that has to be shown via the Pathfinder that this is possible.
Okay, so I have one more question to both of you. Again, coming back to sensationalistic news. James Webb Space Telescope. We've heard again and again that JWST has seen galaxies which are too old for the standard cosmological model to accommodate for. Is it only, some crazy media stuff, or can you really say that James Webb Space Telescope has already even disproven standard cosmological model? Is it too strong to say, or too early to say?
So I'm not observer, but I asked this question to observers, to cosmologists who are observers, and they said that okay, so you have different models of the galaxy formation, and it depends on the dark matter, and we don't know what dark matter is, so there is still some freedom in that. So maybe this is suspicious result for the standard cosmological model, but there is still some freedom to accommodate it within the model.
Okay, so it might turn out something similar to what seems to be going on with dark energy, that it's simply a little bit more strange than we thought, but still it can fit.
Yes, so this is open question now, but it doesn't disprove the standard cosmological model.
Okay, so cosmology, as you can see, seems to be very data hungry. I mean, since it's not. Relatively recently, we've started to get enough data to test our theories, and now it seems that when we start to get this data, we see how much we still don't know. So apart from dark energy and dark matter, what are some major mysteries of current cosmology?
For example, what is the process of inflation? I mean, how did this happen? How was the early universe inflating and generating these small fluctuations? We do have some toy models where we can easily make it, but we don't know. I mean, I think there are of order 100 or 200 models of inflation on the market. Many of them have been ruled out in the meantime, because usually a model of inflation also predicts the amplification of gravitational waves, which we have not seen so far. But still many models work. And then how did the process of reheating happen? How did then inflation end? And ordinary matter and dark matter, how were they produced? And was there something before inflation? Or all of these questions are still wide open.
So, and there is this model by Roger Penrose on conformalized cyclic cosmology, and the inflation is not needed there. Recently, astronomers have discovered this large arc structure, which seems to be agreement with the Penrose predictions. But I don't know, what is your opinion? Is this serious thing when you compare it to inflation, or?
Yeah, my problem with this large arc, there is one or two which have been seen, and if I talk to people who do numerical simulations, they say, yeah, this can be seen also in simulations. One should have, before one says something there, one has to have a better statistical way to measure them, to compare with ordinary simulation. You know how our eye works. We always see things. You look up into the sky, you see the stars forming swans, tigers, everything, And I'm afraid a little bit these large arcs, they are things which we see in the sky, but which are not very well statistically measured. I cannot say how significant they are. I mean, this Penrose theory is interesting. I'm just not entirely sure how well it would answer to the questions which I just posed, or whether it would answer them at all, how ordinary matter formed and, yeah.
Okay, I think it's a good moment to finally pass the questions to the audience. So, yes, please raise your hands. Yes, I see. Oh yeah.
Thank you. Two questions related to this massive gravity model. So first of all, what is the behavior of the second metric when the first one is singular? And the second question, what is the physical interpretation of the geodesic with respect to the second metric? Thank you.
Okay, very interesting question. So if you have two metrics, you of course have to specify, does matter move with, along geodesics of one of the two metrics or even another combination? And all of this has been investigated. There are many, many, many different models. One which I find rather simple is, you see, if you have two metrics, then you have actually 7 degrees of freedom. So you can accommodate one massive and one massless graviton. And so you have more or less one metric which becomes which describes a massive graviton with 5 degrees of freedom, and one metric which defines a massless graviton. Now, if one of the two becomes singular, your theory becomes singular, and I don't know what happens. But so I can only describe the theory when both metrics are not singular, of course. But the question, matter moves along geodesics of which of the metrics, that you have to specify. It's part of the theoretical description. This comes out with your Lagrangian, to which of the two metrics does matter couple. Does that answer your question?
Yes.
Another question.
Good evening. So, since we have a lot of information about the beginning of our universe, but there is part of the journey is the end. And do we have any idea how it is about to end? Thank you.
Yeah, this depends now. If we think a cosmological constant is in the end nevertheless the right thing and just measurements are not good enough right now to see it, if a cosmological constant is there and will stay there, then the universe will become larger and larger and emptier, and in about 200-300 billion years ago, no science like astronomy will exist anymore, because one cannot see anything else than the local group of galaxies. All the rest of the matter in the universe, all the faraway galaxies have moved out of our so-called horizon, and we can no longer observe them. And probably our local group will still contract and become at some point one gigantic black hole. And yeah, after long time, that black hole will evaporate, but that is going to be not billions of years, but much more. On the other hand, if it is not cosmological constant, but evolving dark energy, which becomes less and less important, then there will be an epoch, a future epoch, where we can forget about dark energy, and it was just an intermezzo, which by complete accident is around when we humans are around and wonder about it, but it will disappear. And then what happens to the universe will depend on the fact whether there is positive curvature or not. If there is positive curvature, then the universe will eventually recollapse. And if the curvature, there is no positive curvature, but curvature is either zero or even negative, then it will expand forever. So yeah, it all depends.
But either way, the scenario is rather gloomy.
And maybe let me add that in the Penrose model, this moment when everything evaporates just becomes the new Big Bang, and this is why it's called cyclic cosmology. So.
Yes, this was an idea which goes back to Tolman to the 1930s, who said if the universe would expand and recollapse, it could then expand again in a new Big Bang and recollapse again and could become a cyclic universe, which becomes longer and longer if the entropy grows. If the entropy grows during the entire process, which it does when we form black holes and stuff like this, then there is more radiation in the next universe and the expansion takes longer. And so in this way, Tolman explained why our universe is so big and so old, and I found this a very compelling idea at the time. But now we have no serious evidence that curvature is positive. It still may be positive, but if it is positive, it is still very small now.
Okay, next question.
A question about expansion of the universe. If so, do we have some data about expansion of the solar system?
No, the solar system is not truly expanding. You see, if I say expansion of the universe, I meant on large enough scales, but the solar system is a gravitationally bound system which does not partake in this expansion. Even a galaxy is a gravitationally bound system which does not partake in the expansion. Also, our local group consisting of our Milky Way, Andromeda, the large and small Magellanic Clouds, and a couple of other small galaxies, this local group is gravitationally bound and does not expand. But for example, all faraway galaxies expand from each other and from us. So there are these locally bound structures which do not expand. Also, this room does not partake in the expansion of the universe, or your body does not, because, okay, there are other forces than gravity, but still, this expansion of the universe happens only on very large scales. That's why it took so long time to discover it. It was discovered only in the 20th century.
Okay, next question.
I just maybe want to clarify those two different kinds of gravitons you mentioned and the metrics related to them, I guess, if I understand correctly. You said that they have to operate in more dimensions than the 3+1, right?
No.
No, is that correct? Okay, then maybe misheard. Okay.
They could, but they need not.
More questions? Yeah.
During physical classes, we learned that total energy of the system is constant. And if the universe is expand, the photon should lose energy because Doppler effect. What happened with the energy of the total universe, whole universe? On the other hand, if we have two masses which go longer and longer, the distance between them is longer and longer, that gravity energy should be higher as a potential energy. What is the total energy of the universe? Is constant or not?
Very good question. It is not constant. Conservation of energy doesn't hold in general relativity. It's some people say, okay, the energy goes into the gravitational field or so, but this is cheating. It's just not conserved. You see, without gravity, if you neglect gravity or if you treat gravity Newtonian, then you do have a conserved energy. But the moment you allow for a curved space-time, energy is no longer conserved. The kind of most extreme case is the cosmological constant. This is an energy density which is constant. The universe expands, so the total energy grows as the universe expands. It's not at all constant. For the photons you were mentioning, the total energy actually decays as the universe expands. For those of you who have studied physics and have studied things like, for example, Noether's theorem, which is one of the most beautiful theorems of theoretical physics, which says that every symmetry which we have is accompanied with a conserved quantity. Every continuous symmetry which we have is accompanied with a conserved quantity. Time translation symmetry would be accompanied with the conservation of energy. But in the universe, time translation is no symmetry. The universe is not the same in the past and in the present. So there is no conserved energy. This is something which I think is very important and very not often stressed.
So if I may add something to that. So as you said, I mean, the local energy is not conserved, but when we try to calculate the energy of the whole universe, then there is a problem because we can do that only for asymptotically flat spacetimes. So in fact, this quantity is not defined in the theory. So it's...
So let me just ask. So you're saying that such a thing like the total energy of the universe is not well defined.
Yes, because you have to calculate it somehow, and then you need a definition for that. And this is known for spacetimes which are asymptotically flat, and this simply means that you have some kind of isolated system that goes to the flat spacetime far away. And this is not the case in cosmology.
So it's neither conserved, the energy is neither conserved nor well defined as a...
When you take small box, then you can say it's
yeah.
not conserved because you are just looking at single photon.
Yes,
and
of course.
It change its energy.
Yeah, the energy of the total universe, of the total,
yes,
of the
totally.
entire space-time is not a well-defined concept.
Yeah, exactly.
I finally understood that. More questions? Over here?
Thank you. I would like to ask two questions. First is the discussion about if gravity is carried by some particle called graviton or is just a geometrical thing. Is this discussion relevant for the explaining this cosmological phenomena? And the second question is, do we have some ideas which observable phenomenon could lead to such behavior of the cosmological constant? I mean, this possible change in time.
Okay, the question whether there is quantum, the graviton or the gravitational waves can be really as quantum effects like the photon is not relevant for all observations which we have made so far, is what I would claim. We have seen gravitational waves, but so far what we have discovered is all in good agreement with classical gravity. So we haven't seen quantum effects of gravity, so single graviton effects. But there are people who think about experiments which might see them. They are a little bit futuristic, but not completely impossible. I kind of have forgotten how they go. Do you remember, Sebastian? There have been these suggestions of something which one could do to measure single gravitons, but I'm sorry, I cannot tell you now how it goes. I have forgotten how it goes. So it might be possible to test that, but we haven't tested it, and it's not really relevant for what I told you today about cosmology and for the gravitational waves which have been observed and will be observed in the near future.
So, but let me clarify. But also this modification of general relativity called massive gravity, it also doesn't need quantum effects, right? It's a geometrical theory, not a quantum theory, right?
Purely classical theory, yes, no quantum.
Okay, so
I mean, we always speak quantum language because that's what we are used to, because we have done so much quantum field theory, but actually we can explain all of this also with classical physics. If I say graviton, I mean a classical gravitational wave consisting of many gravitons.
okay, and also because I think that was the second part of the question. So also this decaying dark matter, if this result by Deci holds, it also doesn't need to point to some quantum nature of gravity, not necessarily. I mean, even with this result, gravity might be just a classical geometrical effect and not a quantum particle.
Yeah, I can't see how it points to anything quantum. But of course, the singularities of classical general relativity point to that on small scales something must be different, and we even know at which scale quantum effects must become relevant, whether it is then the graviton itself which is quantum, or whether we have to change this description into something like string theory or loop quantum gravity or so, that we don't know.
Are there any more questions? Oh yeah, over there at the back.
Hello, I have a question which came out after one of question asked about by one of us, and you said that the universe is expanding like 70 kilometers per second, yes, per megaparsec, and megaparsec is like a kilometer to the 10 times to the order of magnitude 17, yes? So how can you say that we are not expanding here in this building when this building is in meters, and if we count 17 times less like magnitude to the 17, yes? Less, so it's less than a nanometer, and still 9 times more, nine zeros more. So how can you say we are not expanding right now? I believe it's impossible.
Okay, first of all, let us go back to this number, 70 kilometers per second per megaparsec. So this means 2 points which are a megaparsec apart from each other, which is, I don't remember how many kilometers, 10 to the 20 or something like that. They expand from each other with a speed of 70 kilometers per second. But this only if they follow the mean expansion of the universe, not if they are glued together, right? If, for example, when the atoms form in the universe, electrons bind electromagnetically to protons, then these electrons and protons, they have a tiny distance from each other, but they do not expand anymore. They are not, they have decoupled from this expansion. So there are always these kind of lumps or pockets where parts of the universe decouple from the expansion and can now be considered as a new point, which is just one little point which expands from all the other points or from all the other pockets which have been gravitationally bound to each other. So in that sense, it's a kind of On average, this expansion happens, but not for each. We cannot take it literally for each point in the universe. So, on average, our universe is one of these Friedmann universes where this happens. But of course, not each point partakes in this expansion. There are these pockets of gravitationally bound objects or otherwise bound objects which do not expand. I don't know how to better explain it.
So I would mention that this question is very famous because there was a movie directed by Woody Allen, Annie Hall, and a small Woody Allen in this movie who plays a boy. I mean, there was a small boy in this movie, and he worried that New York expands and Manhattan expands and everything will disappear at some point. And of course, the answer is not. We shouldn't worry about that.
Yeah, so once again, so if this room had the size of 1 megaparsec, then the opposite walls would try to run away from each other with the speed of 70 kilometers per second. But then again, they are also, I mean, these walls are not just made of gas which does not interact with each other. It's glued one to another. So it's even then it would have a lot of trouble.
One thing you do
expanding.
with that, you assume that there is this Friedmann metric on this scale. And there was a paper from 40s, I think, by Einstein and Strauss, when they studied this kind of a system. So you have a different shape of space-time when you have this room enlarged to this size.
yeah. Well.
Okay, so this is not the Friedmann, it's not the cosmological solution, it's like another solution.
Right.
Yeah, on the smaller scales, of course, then the perturbations away from the Friedmann solution are very
Of course, yeah.
relevant. Order unity.
Okay, so on small scales, it's undetectable.
Yeah, it's different.
Simple as that.
I mean, we use when we describe black holes or so, we use a completely different metric, which locally holds, but on very large scales goes into the Friedmann metric, the metric which describes the expanding universe.
Okay, we still have time for 1 or 2 questions. Oh yeah, I see on the back again, over there. Oh yeah.
So,
Sorry.
okay, if I may, just a probably follow-up question. So you said they might include additional dimensions, right? Would there be any advantages to the theory you described? Would you be willing to take this route to have additional dimension for well-established theory like Einstein's relativity?
I have worked on extra dimensions for quite some time, yeah. So I've thought about them. And many things can happen if you allow for more dimensions. And I even wrote a paper about why there would be only 3 dimensions large if we have a theory which has 11 dimensions, as it was proclaimed for a while. So. But things become so complicated and so many things can happen that it gets very difficult to be predictive. And so I actually at some point stopped working on that because it became just too arbitrary. But it's possible that that is the right way. I don't know.
Okay, final question over there at the back.
Okay, so perhaps that is a stupid question, but what is at the edge of the universe? I mean, our solution says that is perhaps asymptotically flat, but do we actually think about it like that, or there are some cosmological arguments that tell us otherwise?
The cosmological solution is not asymptotically flat. The universe can be either finite or infinite, but as far as we, in our theories which we have, it has no boundary, but this at least spatially. Spatially can be, for example, the surface of a sphere. That would be something which would be finite, but the surface of a four-dimensional sphere, that would be a three-dimensional universe. But then the sphere has to be very, very large so that we don't see it. Like if we walk around in Krakow, we don't see actually that the Earth is a sphere. It looks very flat here. But still we know it because many of you have flown around on these spheres, and yeah, we know it is a sphere. The old Greeks already knew it, or nearly a sphere. But locally one doesn't see it. The same thing might be true for the universe. If that would be true, curvature would be positive, but it could also be, if the curvature is zero, it can be either infinite, like a plane. It's difficult to imagine infinite, but something which never ends. Or it could have a shape like a torus, like how do you say?
A donut
A donut, yeah.
with a hole.
And that is actually not curved, but it's still finite, so we don't know. And the thing is, general relativity doesn't tell us about this global structure of the universe. It can always be globally more complicated, which we would call not simply connected. General relativity tells us very, very little about that.
Okay, if there are no more questions, I think it's time to once again thank our guests, Professor Ruddurer, and Professor Sebastian Szybka. Dziękuję Państwu bardzo serdecznie za bycie z nami do końca i zapraszam na kolejne dni festiwalu, gdzie będziemy się mierzyć z innymi tajemnicami już nie kosmosu, chociaż pewnie trochę kosmosu też będzie. Serdecznie zapraszamy i dziękujemy.